a stronger gravitational pull on its surroundings, so it pulls more stuff in, which means it's more massive than its surroundings, which means it has a stronger gravitational pull, which means it pulls even more stuff in. This is a runaway process. Once gravity gets going, the regions that are a little more massive than average get even more massive and continue to grow and grow and grow. And this is the fundamental way that gravity takes tiny differences in density at the time of the Big Bang and turns them into the enormous differences that we see around us today, with galaxies and stars and planets and even black holes, extraordinarily dense. Years across, this movie is about 1 million light years. This panel shows the density of gas, and the color is a little different. So now dark means lots of gas. This panel is the temperature of the gas. So red is hot. And what you see, again, you see dark regions pulling stuff into them. You see little clumps falling, raining in. You see occasionally explosions where stuff is actually spewed back out of the galaxy. That's a consequence of when stars start to form in galaxies. Massive stars at the ends of their lives explode in these dramatic explosions called supernovae. And those explosions of stars are actually sufficiently powerful to actually blow gas all the way out of an entire galaxy. And that's what you're seeing in this computer simulation. And so, in detail, understanding how our galaxy formed is actually rather complicated, because we have to understand how the stars form, how stars die, how gas gets into galaxies, how it gets back out through these cataclysmic galactic explosions. But the essential idea for how galaxies form, for how stars form, for how we went from the smooth Big Bang to the lumpy universe today is this basic idea of gravity causing the rich to get richer. The denser, more massive regions have stronger gravity. They pull more stuff in. That's a runaway process. And that leads to the formation of the remarkable variety of galaxies, etc., that we see around us today. We think within our own galaxy. So now I'm going to zoom in. I'm going to show you another movie which will look in many ways indistinguishable from the previous movie. The primary difference is that this movie is now actually just a few light years across. This is not a movie of how a galaxy forms. This is a movie of how an individual cloud of gas within a galaxy, how it forms stars and planets. As gravity causes the dense regions to pull stuff in, pull more and more stuff in, you'll notice that because the stuff doesn't fall straight in, because it has a little sense of rotation, you get these nice disk-like structures, which lead to the fact that the planets in the solar system are all in the same plane. That's because they form out of these rotating disks like you see here. But really it is the kind of central role of gravity takes matter from the very smooth state in the universe at large, and the gravitational force crunches things together until you get down to the scales of individual stars and individual planets, when there are things like nuclear fusion, which is able to keep the sun hot enough to stop gravity from shrinking the sun even further. Okay. So that's in some ways a 4-slide summary of about 3 years of graduate courses in astrophysics on how stars, galaxies, planets, etc. We're particularly interested not just in how do stars and galaxies and planets form, but in particular, what about planets like our own? Planets that have a solid surface and that have temperatures that could support liquid water. And just in the last year, there's been the first real unambiguous set of detections that tells us how common planets like our own are. And this was done with a telescope called the Kepler telescope, which was actually run out of the NASA Ames Research Center in Mountain View. And Kepler basically did this for 4 years. It looked up at a bunch of stars. It measured the light as a function of time from hundreds of thousands of stars on the sky. And it watched for the rare times when a planet passed in front of the star, dimming the light of the star just a little bit. And then as the planet progresses across, once the planet passes in front of the star, the starlight goes back up. And then this pattern repeats itself as the planet orbits around the star. This technique is the major technique that has been used to detect very small planets, planets with sizes comparable to the size of the Earth. This technique allows you to directly measure the radius of the planet. The reason is that the decrease in the amount of light that you detect is directly related to the size of the planet. And so you can measure, by measuring that decrease in the brightness of the star, you measure the radius of the planet. And so there's been a lot of beautiful work being carried out with Kepler. I'm going to highlight some of the work done by one of the graduate students at Berkeley, Eliot Quataert, who actually was an undergrad at Berkeley as well. He did really the first careful systematic survey to figure out what fraction of stars, like the sun, have planets like the Earth. And what does that mean? That means planets like the Earth means sizes similar to the Earth, so they're probably rocky planets, not big gaseous planets like Jupiter. And planets like the Earth also means orbiting at a roughly similar distance from the sun, so that the planet isn't too hot, which happens if it's really close to the star, or too cold, which happens if it's really far from the star, because too hot and too cold aren't conducive to liquid water and life as we know it. And the amazing thing is if you even require those rather stringent constraints that the planet be pretty similar to the Earth in size and orbital period, what they found is that about 20% or so of stars like the sun in our own galaxy probably have Earth-like planets. And that's really an amazing number. That means that there are literally, billions of stars orbited by rocky planets that likely have liquid water in them, just like you. And that's a pretty amazing result when you start to think about trying to understand scientifically the question of, are we alone in the universe? Is there other life in the universe, other technologically advanced life, quote, intelligent life, etc.? That question, which has really been the domain of theologians and philosophers, is now a question that we're beginning to answer some.